different things focused on multi-scale modeling of heterogeneous catalysis, porous materials, as well as transport and reaction interfaces. His career has spanned several institutions. He has been at University of Virginia at Charlottesville. He has been at Pacific Northwest National Laboratories, and most recently, he is at Tiangong University. So while he sets it, please join me in welcoming our keynote speaker. Okay. It is a 40-minute talk, by the way. So it says 20, but it is 40. Okay.
Thank you. First, I want to thank you, the organizers, for a very nice introduction. Just like you said, many institutes that have so clear, so American and now in China. So I'm also very pleased today to have this opportunity to talk about some of our research work on the NOx reduction. The topic I want to explore today is the circular inside picture ammonia system with selective catalytic reduction using the Copper-Exchanged Small-Pore Zeolites. So as you're aware, the NOx is one of the major route for the haze, photochemical smog, and the acid rains. So then most of the NOx actually from the diesel vehicles, which only account for 10% of our all automobiles, but produce 90% NOx, and roughly total about 6.4 million tons every year. So how to limit this huge amount of the NOx is very important and urgent. So there are several different programs actually worldwide trying to deal with these programs, such as the STAR program, US, and the Horizon 2020 in Europe, and also in China. That's maybe more severe. It's kind of China trying to implement the final systems for emission control, particularly for the heavy-duty diesel vehicles. So in order to eliminate the NOx, we have the system these programs to show. The after treatment systems actually include 4 setting units. The first one is desulfurization catalyst, DOC. Try to oxidize the hydrocarbons, COs, and try to eliminate this kind of stuff. Then we have a diesel, particularly filter, try to capture and filter particles in the emissions. The third part is we are focusing on the something reduction called C. We try to use ammonia to convert to negative and water. The last part is ammonia oxidation catalyst. Why? Guys, the ammonia slip from the single unit. We can run more extra ammonia. For these whole systems being implemented, the diesel in vehicles for long term. So around this moment, so exchange small-pore zeolites such as carbon-13, which patented in 2009, is found to be the one against the ammonia system SCR catalyst because they have outstanding DNF efficiency and higher hydrothermal stability and boiling resistance. So try to improve this type of the copper-exchanged zeolites and use the SCR reactions. We actually should gain more fundamental understanding structure, composition, activity, and the range relationship. That's because for the SCR performance, all particular hydrothermal stabilities depend on the various factors. For example, if we have a higher silicon-aluminum ratio for zeolites, we definitely will have higher stabilities for zeolites before you have more silicon on the framework. But if you substitute the silicon with the aluminum, you get bronzic acid side. Then you have carbon there. Carbon can exchange this bronzic acid side on that bronzic acid side positions. So the aluminum silicon-aluminum ratio actually, or aluminum locations actually determines how much carbon you can exchanged in the zeolite catalyst and where the position of these carbons. So, and this holds kind of different factors on the performance and the stabilities. So, what is most important, actually, I want to talk about today is how water affects the ICR performance, and another is we put the metals, just like sodium and the lithium, to see how that also affects stability, hydrothermal stability, and ICR activities. So the first part we are talking about is water ammonia roles on the low temperature ammonia. So water normally people think, if you do the zeolite catalyst, water normally people think have a determinatory kind of effect on the hydrothermal on the zeolite stability, because water can do the dehydration. So that's a great framework and it's how. But recently, we just use water. We actually find the water not just do the fancy. Actually, water can locate the LCR performance. As you can see here, we use the Copper-Exchanged LTA catalyst. If you put 10% water in the field, you can find the green line actually is the wet condition. We can put some water in here, and the purple line actually the dry conditions without water. You can see the endo conversion is actually about 30% and 20% at a different temperature, and the lower temperature is a little bit higher, about 2% higher. And then if you have the water in the symptoms. This is also depend on the different silicon aluminum ratios. The silicon aluminum ratio, the 16, give out the best reports. So this is from an experiment, just know why. Normally people think what did not involve any reactions or do the bad things on the zeolite structures, right? Do the aluminum tests. But actually you found is the opposite. What we find is water actually can promoting this kind of at their performance. So we tried a different kind of crash catalyst also at high temperature about over 1,000 K 80, thermal 80 conditions. But actually, this is not just for crash catalyst, it's also happen for HTA. If you have a high temperature 18%, they still can actually promoting the SCR performance. And we also started how this couples, different couple species, just like we normally know in the copper-exchanged zeolites, two types of active copper species. One is the copper hydroxide, it's copper OH, which normally located with associated with one alumina and in the 8 membranes, and also copper complex as normally with associated with 2 alumina for that charge position. So that's in 6 membranes. We found that these ratios actually also affect the activity, just like we shown here with the thermogrammetry. As you can see, above the 0.2 ratios, actually, if you go to the higher copper and higher thermogrammetry. On the other side, for the aged, this kind of catalyst, actually, if you go to the lower this kind of copper oxide, you will get higher thermogrammetries. But eventually, you get normally same kind of parent activation in about 35 kilograms more. So this is also from an experiment. Then we just want to know why. If you put the water in there, we get this kind of different performance. First, we started, for the PCR, ammonia system PCR catalyst. If you do this kind of catalyst, the chemical actually solvent by the ammonia and the lac framework. So we want to first start it how the water put the water in there and the water and ammonia or cold solvent the lac is with using carbon hydroxide. You will see both ammonia and water solvent the carbon hydroxide and definitely ammonia with the carbon hydroxide is more stable and with the water but both of them actually we think can coexist. And if you're dealing with with six-member with an actually focus on real ions. So for the new species, and this kind of new species also play a big role in the SCR performance. So based on this kind of the knowledge, we actually proposed a new kind of interaction intermediate is associated with the one hydroxyl and ammonia, not just normally I read it here is in the red one. That's normally people think copper plus with two associated with two ammonia is a reactive species in the SCR reactions. So we have calculated this kind of redox sections. If you can see here, actually we use one still the two copper plus to do the reactions. The left side is oxidation circle. I'm not going to detail about this. And the right side is the redox. So this is the new mechanism with the water. So with the water, we also have the four different kind of the reaction intermediates. As you can see, the number one is in the upright is up left is with copper with the ammonia. Then we have a different combination is the water one and maybe the water with side and trans. So a different kind of configuration. Different configurations do the same cycle like I show you the after PPT. You will see actually the new reaction intermediates with the water have the lowest kind of the reaction barriers about 82. Initially with the two ammonia that's without water, we have 150. So we calculate based on this free energy barriers. We calculate the thermal frequency. We find actually with the young species with the water associated we have 8 times higher order for the HCl reactions. So total reaction rate is increased. That's the reasons we find actually experimentally to find 30% and 30% here at the low temperatures. So this is the reason we do the calculation. We try to explain why we experimentally find this situation. We also find that water is not just involved in the reactions, just like I said, water, all the new reaction mechanisms. We also find actually if you put water in the filters, water can help the copper ions can move all magnesiums. And I show here, if you have no water, you have if you move the one copper ions moving from one cage to another cage. Here I show you from the ATI cage to the salt cage. In the higher tier zeolites, you will find the barrier about 183 kJ/mole. You put one water associated with the copper ion, the barriers will lower. The first one actually is even higher. Second one, part two, is 183 kJ/mole. If you put two waters in there, that barrier is lower to 112. That means if you have more water, solvent with the copper ions, the copper ions can move from the one cage to another cage. This is not just for moving the copper ion. This is also we did that from some outward position. If you have a copper species ions in the unaccessible positions in the zeolites, you can move. If you have water, you can move this copper kind of species move to the to another more open species. So reaction happens there. So this is the second role for the water promoting. If you use the water in systems. So the third one, if you have the water, we also find water actually can help the copper self-reduction process. That means copper can reduct from the 2 plus to the 1 plus. If you have water, actually we need to go to the top one. You can find actually the copper can easily, much more easily can change from 2. So finally, we find that also the hydrothermal quality change. So if we do during the hydrothermal process, so normally carbon hydroxide will be combined and forming the. So here we show if you form the carbon oxide during the hydrothermal treatment, then if you have the water can also break down the form the carbon oxide Here I just showed one example. If I use a carbon dioxide trimmer as a starting kind of the particles that's already from the summer aging conditions. So it have water in there, actually water help this carbon dioxide dissociation. As you can see here, without water, the carbon dioxide trimmer, if you have reached the dimer and a monomer, you need overcome 246 kilojoules per mole. But if you have one water associated with this decomposition process, the barriers will lower to 162. And also, if you have more water for the two, so if done for the two waters, the barriers continues lower, okay, and it's three waters. So we actually calculate a series of these things to find actually what the do can help to dissociate the carbon dioxide, this kind of big particles during the hydrogen emissions. After break up this, actually the carbon dioxide can easily convert to carbon dioxide to create a new active site. That's also the one reason we find theoretically why we observe the promoting role for if you put a little bit of water actually in the systems. Okay, let's summarize the first part. So the principle of the water molecule actually finding mostly the low temperature ammonia SCR activities. We find that several reasons for that. One, we find that actually the new reaction intermediates associated with water and the new reaction mechanics. Second, we find water can change the copper ions locations in the LTA, actually create a more active site by water assistance and migrations in this kind of copper ions. The third is water also can help the self-reduction process, also can decomposition the carbon dioxide which formed during the hydrogen aging conditions. Okay. Now next we will go to the second part. We're talking about the effect of propan, ammonia, and the selenium on the low temperature ammonia SCR performance. So we also starting from the experiments. This is also the experiment we just did about 2 years ago. Actually, we find put some samarium. We put in the Copper-Exchanged 13 zeolites. We find it actually also increase the low temperature SCR activities. Here is the result. As you can see, for the pure samarium SiC13, it's very kind of poor kind of SCR activity with only the absolute maximum about 15%, right? The purple line there, that's lower, that's samonium SiC13, samarium SiC13. So if you put samarium into the SiC13, so you'll find actually all these kind of samples is better than pure copper SiC13, particularly at low temperatures. If you take out the 90% I showed there is the T19, that means no conversion reached the 90%. You can see the temperatures for the pure copper SiC13 about 250. But you have put some samarium there, the temperature is only 2200, so you can reach 90%. So for the same temperatures, actually, generally you can have 10% this kind of wall no convergence. If you put some more samariums into the top, that means the second co-cations have their main role in the low pressure ammonia as their performance. Also, this can happen for the hydrothermal aging catalyst. If you if you want HDL, you do the same thing. You have the samarium and put in for identity 13. You'll find similar kind of situation. But definitely, obviously, you can see the increase of the performance thread catches. So we also think we want to know what happens if you put the samarium actually in SiC13. We actually find it's do kind of the location of two active species, just like we talk about the copper hydroxide, CuOH, 2 plus. If you put the more kind of the scenario in there, we actually find we get more of that's more most active species cover, more active actually than cover class. You see here the blue are actually increased if you increase the scenario kind of the impact in systems, and the red bar actually the contrast the lower. For the people side is only for the figures of aging, you will find without when actually they jump from too fast from the turbines. But if you put scenario in there, you still gonna have 78. You see there's the blue bar there. That's also the copper hydroxide. That's also the most active species for the active ammonia. So that's also the reasons we find actually for the co-cations scenario actually can change the couple the concentrations. That also means changes the locations of the different copper ions. So this is actually from the our another experimental characteristics. We actually use the XRD and XTM try to find out. So if you put the samarium in the systems, where are they? So actually, you find actually they are also in the six member rings at the same positions with the copper 2 parts. So this is a experimental result. And we calculate if you have the samarium oxide, actually, we still have to keep the 2 plus charge. If you want to put the six member ring associated with 2 alumina, you will find actually the existing existence, the ammonia oxide, hydroxide, do affect the most active sites, that's copper hydroxide. And through the charge transfer, we find if you put the samarium hydroxide there, actually your the most active species, copper hydroxide, get another. So the charge actually get the length, the charge change from 1.07 to the 0.94. And also more Scenario hydroxide also gets some no some electron. So they are cross between the two of the side to the scatter. So this is the electronic not active cell. So we find also if you put the thorium in the system, it's also enhanced of the systems. We calculate different situations. Like one, actually, you see that the pure actually system, even without the neighboring the power two part. The blue line actually is with the two part number species in 6 member rings, and the red one actually is with the Samorin hydroxels. So we will find if you have more Samoria in the systems, the barriers for the double hydroxide science formation actually became difficult. That's also the reasons you will find actually if you put samarium ion into the systems, you will get better stability. Now we think we experimentally we found samarium ions actually in the 6 membrane, but copper 2 plus also in the 6 ring. So which one is preferred? So then we calculate these two different ions. We find actually samarium maybe thermodynamically and kinetically more preferred on the 6 membranes. That means if you have a samarium, whatever you put in first or in the second, it will take the 6 membrane positions, then replace the copper 2 plus. So the whole thermodynamics you see is a downhill and the area is low. But if you do the backwards, if you just, for example, if you have a small hydroxide already, take the 6 membrane, you put the copper in the next, that's kind of when you make the catalyst, you can do the different sequences for the two cations. And in the systems, you will find the copper 2 plus cannot, exchange replaces ammonia hydroxide. That means ammonia hydroxide in the 6 membrane is very stable, and that's a place also consistent we observed experiment. So with this ammonia, we talk about the positions and the reaction conditions. We also notice they have to be solvated by the ammonia. That means without a lot of the ammonia, these three species now we have not like the initially only copper exchange the zeolites and the phenols also can be solvated by the ammonia. So we calculate the free energy of this solution process. Actually, we find when the ammonia hydroxide still the stable one, and the copper hydroxide is a non-stable, is least stable one. The copper for us is just in the middle. You will see actually the top um, ammonia ions actually is really, really stable and is not involved. That also means it's not really involved in the SDR reactions. It's just affects the copper species distributions and its concentrations. So if you have the copper species, we actually do another kind of reaction studies. We use a computational, we use AIMD, try to understand if you have the copper one associated for ammonia molecules, how they can migrate from one cage to another cage because when we talk about the reaction mechanism, which means the two coppers solved by the two ammonia or either one ammonia with water, they have to meet each other and then form the kind of the new structures to do unseen reactions. Let's ask the couple associated with ammonia can freely transport between the different cage. So we did that actually using AIMD. We found the two different structures is very stable, and these two structures actually can exchange. So when you transfer them, if you have a whole ammonia associated with the copper, actually it's too big, the size is too big, so actually cannot transfer, migrate, go through the windows. So the two ammonia have to be uh, detached. So from this molecular complex, and you can see here, if you have a bronzic acid there, actually it's two ammonia out. Then you just left the copper hydroxide is associated with one ammonia molecule. That's the size you can go, through the cage, from the window, 6 membrane or 8 membrane. You can go to this kind of windows from one cage to another cage, and it's straight. But in the whole ammonia associated, it's difficult to move different kind of cage. So next, we have this kind of ammonia solarium kind of co-cations in the systems. We actually also calculate how this creating the second one cations affect the reactions. We calculate, and you can see here, we compare the copper 2 plus with ammonia hydroxide. They all both, occupy the 6 membrane. You can see actually when you have the samarium hydroxide, the plug here, the barriers from the reaction intermediates, that's the most important reaction medium in ICM. Ammonia nitride, actually much more easy. Barriers are only 31.4. And if you just only have a normal 2 plus, the barrier is 56.7. So that means ammonia also, they are not involved in the reactions, but they do kind of affect the barriers and change, just lower the barriers for the most important species. Another important species we check is natural cyanide. So H2NO, we find the similar situations. If you have a ammonia hydride hydroxide and 6 membrane, you will find the barriers also lower, from the 69.7 is lower to the 39.5. So that also means that the Samoria, if you're aiding the Samoria in the systems, actually do change the reactions barriers and lower the barriers and increase the performance. Okay, so this is a summary. So next to actually we think how about counter cations. Another thing is also what people like to do to put in the copper-exchanged zeolites. We also studied this. It's very similar to the case we just talked about, but has also the different situations. Actually, we find if you see here is a has a different from the kind of performance with we put samarium in. They do have some changes, the low temperature, but not in the below the 300 or maybe 350 temperatures. Most of this kind of the enhanced performance is happened after 400 degrees. You can see there the blue line, the red line, they are higher than the black, which only the pure copper exchange with the SS13 zeolites. But for the pure kind of the lanthanum, the SS13 also there's no kind of very poor activity for the SCR reactions. But it's not like samarium is do see a big change actually in the initial, particularly below the 250 thesis. And also, but it's also happened for the hydrothermal engine catalyst. You will find actually the performance increase happens actually in about 400 to 550 thesis, not in the lower temperatures. So this is different from samarium additions. So we want to know why. This is the same kind of the loading actually we did from the samarium. But then we started calculate if we change the copper loading, what happens? As the previous one, as you can see, we use actually 4% copper, which is the copper 4 there. Here is the copper 1% weight percent and 2% weight percent. Then we find the difference. So actually you can see here, if you put the less copper in the systems, you also put the lanthanum there. So you see there's a big difference between if you have lanthanum or without lanthanum, right? So also you can have the 4 lines actually. This is happening in the whole low temperature windows from 150, from 200 to 550. And also happens for the hydrothermal agent, this kind of catalyst. So this means lanthanum also can affect the SCR reactions, and also promoting the SCR reactions if you lower the copper, and you cannot also put too much kind of lanthanum in because as you can see here, the blue line there is we put too much kind of lanthanum, it's wrong the structures, and you get actually without really good SCR activities. Similar thing, if we put the lanthanum there, we try to theoretically understand where the lanthanum is. And we calculate, like just last case, we calculated how the lanthanum is the copper 2 class, copper class and oxide, and 6 membrane or 8 membrane actually we find the lanthanum is different. Lanthanum is different. It's actually stay in the 8 membrane, not 6 membrane, just like 6 membrane. So we calculate the delta T, we find actually lanthanum hydroxide, and that's actually the real kind of the species. Yeah, actually 8 membrane, and for us is 13. Now we find actually why the lanthanum actually one stand is performance change, and another is the hydrothermal stability change. We find actually if you put the lanthanum hydroxide there, actually if we calculate the dealumination process, we find the first aluminum oxygen barriers and the last aluminum oxygen barrier bond breaking barriers. It means if you put a little bit of lanthanum into the systems, you actually also kind of enhance the hydrothermal stabilities against the water. Also, you also stabilize copper 2 plus. You also calculate the copper 2 plus, hydroxides with water to form the copper hydroxide. And if you put the lanthanum, then also because the copper 2 plus the 6 membrane. So we actually find it also increase the barriers for copper 2 plus convert to the copper hydroxide. So this means if you put the lanthanum in the systems, they also stabilize the SS13, copper exchange SS13. Okay, Finally, I just want to summarize the second part I'm talking about. We put the different cations, try to understand what is cations affect their performance, also the hydro thermostabilities. This is the two important properties we want to improve. We find actually this is also very similar or kind of the same scenario. It's affect the carbon distribution. It also affects the copper oxygen state if you put the lensing into the system. Also, we can find actually it's also affecting the hydrothermal aging conditions. If you have lensing, they are just like we said, the copper to glass easily go over to the carbon hydroxide, finally go to the carbon dioxide. So this is all I want to talk about today. And finally, I just want to thank the students, Wen Bianxue and Wen Ru Zhao, and do the most of the DIT calculations. I also want to thank my experimental collaborations and Ji Hongyu, Professor Ji Hongyu, who from Jilin University, and Professor Su Banghong from the PostTech in Korea. And this project actually is funding national natural science.
Different things focused on